Hello everyone. This video is to show you how to complete a simple linear regression and / correlation model in Excel and how to interpret it. So before we start, remember that an independent variable is your X variable that's explaining some sort of variation in the Y variable. So your X explains something with your Y. In chapter 14 and in this video, we're looking at a model of y equals beta naught plus beta 1x, where your beta naught is, so this beta 0 is your intercept, and your beta 1 is the correlation coefficient of that variable. Chapter 15 and the next video will deal with the multiple regression model you see down here. So when we look at a simple regression analysis, we are trying to figure out what type of relationship we have between our independent and dependent variables. We're trying to be able to predict our Y variable or our dependent variable based off of our X variable or our independent variable. And again, this is just the population, so that's why you see the big betas versus the little betas. Our goal again is to estimate those betas based on a sample of ordered pairs. So what we're actually looking at is these type of hypotheses. Either there is no positive relationship between X and Y, or there is. So that's our original hypothesis. So here we go. So we've got this data, and we're going to look at sales and inventories and sales and accounts receivable and see if we think sales is going to have an effect on either. So just like chapter 14 starts, we're going to start with some scatter plots. So we're going to highlight sales and then inventories because sales is going to be our independent variable. And we're going to insert a scatter plot. Again, yours may look a little different based on if you're using a Mac or a PC. And we kind of see maybe a little exponential curve there. Not sure if that's exactly a linear regression analysis that we should look at. So let's try sales, and I'm using the command key to get these on accounts receivable. So again, let's insert a scatter plot. That looks much more linear, and we can even check it by inserting a linear trend line. That looks pretty close. Let's make that a little bigger. If we insert a trend line on this one, it's not quite as close. So let's look at a simple linear regression between sales and accounts receivable. So again, remember my null hypothesis is that all population coefficients are equal to 0, meaning there is no relationship between the independent and dependent variable. All right, so that's our first one. So then our alternative hypothesis, let's add a few in here. There we go. Is that all population coefficients are not equal to 0. So it's the same thing except for with a not in there. All population coefficients are not equal to 0, meaning there is a relationship between the independent and dependent variables. All right, so let's merge and center those. All right. So those are my null hypothesis and my alternative hypotheses. There should be an S there. All right. And again, remember how you can look back here to see that's how you write them in notation form. All right, so let's actually run this linear regression. So we're going to go into data analysis. Out of your tools, you're going to pick regression. Click OK. And then we've got to determine our y and x variables. So we'll restart all of this. So remember, we're looking at what effect does sales have on accounts receivable. So accounts receivable is my y, because we're trying to see if sales has an impact on accounts receivable. So that means my x, my independent, is sales. Want to make sure we have labels checked. For output, let's just put it in F1. And then we want our residual plots. We do need to check for normality, but don't use the normal probability. That's not what we're looking for. So click OK. All right, here we go. Actually, let's move this over one or two, so that way we can see them all. Oh, this one's just growing. Okay. Let's move this back. And this one. All right. So here we have our output of what the regression model gives us. So we start with looking at this multiple R. That's our sample correlation coefficient. This R squared is our coefficient of determination. This is the one that we look at to see how much of our sample is being described, or how much of the variation of our dependent variable is being described from our independent variables. So 80.9% of the variation in accounts receivable can be explained by the model that we created. So we'll get back to that in a few minutes. So again, that first thing we need to look at is that null hypothesis of all these population coefficients being equal. So how do we determine that? Well, we look at our ANOVA analysis and that regression F statistic and the significance of that F statistic. We can already see right here that that significance is 0.037, which is below 0.05. So at a 95% confidence interval, or an alpha of 0.05, we can reject the null hypothesis and claim that all population coefficients are not equal to 0 and that there is a relationship between those two variables. So there we go. Reject the null hypothesis. Put that in right here. Make it easier to see. Woo, that's a lot. We don't want to go that far down. There we go. Reject the null hypothesis. All population coefficients are not equal, meaning there is a relationship. So that was the first thing we wanted to check on. Let's move this over here a little bit. There we go. All right, the next thing we want to look at, since we now know that that is true, we want to look at our coefficients. The nice thing about the regression analysis gives you your coefficients right there. They're very easy to find. So what this is telling us is that when we look at our model, when we try to create the model, we're using those coefficients. So when we look back at the PowerPoint, oops, and I just closed it. Let me reopen it. Sorry, it'll take a second. There we go. When we look back here, we're trying to create this model that has this equation format, or this equation format. This EI is just the error term, so the residual as it's called. So what we're going to do is we're going to type our equation as y equals our coefficient for the intercept of 62.43 plus our coefficient for sales, we'll say 0.97x. And that's it. That's our model. And if you want to interpret this, we would be saying that 62, if sales were 0, we'd still have about $62 in our accounts receivable. Probably, I know this might not make sense thinking about it that way, but that accounts receivable could be from a previous month or something like that. And what this coefficient of the x variable is telling us, that x variable is sales. They're telling us that for every increase in sales of $1, we add about 10 cents or 9.7 cents to our accounts receivable. And how this is useful is that you can actually type in different amount of sales to determine your accounts receivable. So y equals that, but let's, instead of the x, let's say, what if we were looking for $2,700? Well, by just typing in the actual equation, whoops, not that, equals 62.43 plus 0.09 times 2,700. Oops, it should be 97. If we were at about $2,700 worth of sales, we would predict that our accounts receivable would be at $324.33. So that's how you can use the model to actually make a prediction. Now, we have rejected that null hypothesis, saying that our coefficients are not equal to 0, so there is a relationship. So when you do that, you need to also come down and look at the p-value of your actual variable, which is sales. And notice that that p-value is below 0.05. So again, we can say that that coefficient is different than 0 because we're seeing that the p-value there is significant, which is the exact same as it is for that F statistic. And these two are the same because we've only got one independent variable. The p-value of the variable becomes more important when we're dealing with multiple regression. So now that we've got our rejection of the null hypothesis, we've stated that there is a formula, or excuse me, there is a relationship between these two. We're saying that our coefficients are not equal to 0. We've been able to establish that about 80.9% of our variation is covered by this model. So it's a fairly decent model. Now we just need to check to make sure that our assumptions of regression analysis are held. So we've already seen that we've got a scatter plot that appears fairly linear with accounts receivable down here. So that's the first assumption. And if you're looking for these are in section 14.6. The next assumption is that the residuals exhibit no patterns across the values for the independent variable. So if we look at the residuals plot that we had created with our regression, there doesn't appear to be a pattern. They don't look like they go in one direction, either linearly positively, linearly negatively, in an exponential form. They just look like they're scattered. So that looks good. The third assumption is that our variation of the residuals is the same across all values. So what we're looking at is, do these values vary amongst this 0 the same? And we only have 5 points, but if you look at it, these two are about the same distance away. These two are about the same distance away. So they're varying the roughly the same amount across that horizontal axis. So that third assumption can be said that, yes, we're good with that. Now the fourth assumption deals with that normal probability plot. So in order to create that, we need to use our residuals, and we have to create z-scores for those residuals. So if you think way back when we did z-scores, we need the average of our residuals, and we need the standard deviation. Oops, not the population. pass of our residuals. So this is our mean, this is our standard deviation. Now we create our z-scores and we use the standardize function. And we're going to use each individual residual and the mean of the residuals, and we are going to absolute reference them, so the mean and the standard deviation do not change when we drag this down. So standardize our residual with our mean and our standard deviation as absolute referenced. Hit enter, drag it down. So now to see if our regression analysis passes for normality, we need to create a scatter plot of the z-scores. And I'm going to use the command and put z-scores on the x-axis. And then create that scatter plot with the z-scores and the residuals. So we click Insert, Scatter Plot. And if this is normal, they will form a straight line or close to a linear line. And it sure looks like they're real close. This one's a little high, but they're close. So we're going to say that all of these pass the assumptions made for a regression analysis. So again, what this is telling us is that ceteris paribus, all the other things equal, if we don't change anything else, any increase in sales by an increase in sales by $1 will increase our accounts receivable by about 10 cents. We can also see that we've got, and I'm not sure why mine is giving me 2. We don't need 2. But we've also got our confidence intervals of how we think that's going to vary if you need it. But overall, this is a great way of coming up with not necessarily a firm prediction, but it can give you some sort of an idea of what to expect. And it's used in lots of financial analysis, not just with sales and accounts receivable, but a lot of different things that you see on those financial statements can be applied in this method. If you have any questions over simple linear regression, please let me know. And the next video will go over multiple linear regression.